All right, I guess we have reached the 3 p.m. mark, if I'm not mistaken. So welcome everyone. And as I said before, I'm delighted to see many who have already done their duties yesterday back for the second day. I know that this cannot be taken for granted, so thank you very much for that. And I guess without further ado, we get started into the second day. And as you can see, the first paper is called Information-Driven Volatility. It's going to be presented by Leyla, but Hengjie is also here, which is very nice. And I think if there is nothing else that we have to settle or discuss, I think Leyla, you can go ahead for a 20-minute presentation. The rules are the same as yesterday. Great to have you with us. Please go ahead.
Thanks for including this paper in the program. My name is Leyla. I'm Syracuse University. Co-author with this paper is co-author with Hengjie, University of Minnesota, and Leyla from Boston University. So let me move on to the motivation of the paper. So the risk-return trade-off, or this volatility and expected return trade-off, is perhaps one of the most fundamental concepts in finance. And standard consumption-based asset pricing model with stochastic volatility typically implies a positive relationship between the past realized volatility and future expected. However, empirical evidence often finds a negative correlation between this past realized volatility and future expected. The purpose of this paper is to propose a theory of information-driven volatility. Theoretically, we show that information-driven volatility induces a negative correlation between the past realized volatility and the future expected. We develop a model based on this insight, and we show that our model can find several volatility-related empirical facts that are often positive from the perspective of standard asset pricing models with stochastic volatility. To understand this puzzle, note that any model with no arbitrage implies the risk premium should be proportional to covariance between the return and the stochastic volatility. Between the return and the stochastic discount factor. So here I write this covariance as the product of the correlation rho and the expected volatility of stochastic discount factor and the expected volatility of future. So if I hold this correlation constant, the risk premium must be proportional to expected future volatility. So this condition holds for all models with no arbitrage, including our model. What differentiates our model from traditional models is that traditional models rely on time-varying volatility to macro fundamentals to generate stochastic volatility, whereas our model does not. In the standard models, since such fundamental volatility is positively correlated, so past realized volatility positively predicts future volatility, and therefore the no arbitrage condition implies a positive relationship between the past realized and the future. Well, it is this positive correlation between the past realized volatility and future expected returns that we're questioning. So we show that if the volatility is driven by information, past realized volatility negatively predicts future expected volatility, and therefore future expected returns, which is consistent with it. So in the interest of time, let me skip my literature review, and let me start with the motivating facts for our theory of information-driven volatility. The documentation of the negative relationship between realized volatility and expected returns dates back to early 1990. For example, both Nelson, 1991, and Gloston, Jacobson, and Rankford, 1993, both documents a negative correlation between volatility and expected return. Most recently, Rera and Moore, 2017, constructed this volatility managed portfolio, which is a portfolio that increases leverage when realized variance is low and decrease leverage when the realized variance is high. So they show that the volatility managed portfolio, which is this red line, earns an extra premium of about 2% per year relative to buy and hold market portfolio, which is the black. So they pose this as a puzzle because the extra premium of this volatility managed portfolio is another evidence for the negative predictability of future expected returns by the passive director. To reconcile the above puzzle, our model has two critical theoretical premises. The first one is that over short horizons, and short horizons meaning daily, monthly, or quarterly horizons, the volatility of the stock market is more likely to be driven by information rather than the volatility of macroeconomic fundamentals. But in general, stock market volatility can be driven by both. To understand the difference between fundamental volatility and information volatility, we consider the following variance decomposition formula in this. Okay? To think of stock as a claim on consumption that realizes a big time in the future. This total variance of consumption equals the sum of variance of this conditional mean and the expectation of this conditional variance. So the information here is denoted as S here, at time small t, which happens before the time big time, the big. Traditional stochastic volatility models assume a time-varying volatility of macro fundamentals directly to assume the left-hand side time varying. However, because macro volatility is unlikely to move at high frequency, I want to fix this left-hand side variable fixed, right? I want to hold this one fixed and impose shocks to quality of the information. So holding the fundamental volatility fixed in our model, a more precise information triggers a larger movement of the financial market, which corresponds to a higher volatility of this conditional expectation. So this term is higher, and therefore the volatility of future returns on average, the second, must be lower. Okay, this is what we call the information-driven volatility. The information volatility is what? Information-driven volatility refers to the fact that a time-varying informative of the information S induces a negative correlation between the realized volatility upon the revelation of information and the expected volatility. Okay, now let me show you the empirical support for the first theoretical premises that we proposed. The stock market returns over short horizons are unlikely to be driven by this volatility of macro fundamentals. So at the same time, information arrives continuously at the market, and so it is more likely to impact our financial market. In the top panel, the blue line is a monthly consumption growth process, where the red line is the monthly stock market. And the bottom panel is the estimated conditional volatility for both states. So clearly, we see the volatility of consumption growth does not change that much. But while the volatility of stock market varies substantially over. So the realized volatility of macro fundamentals is unlikely to be responsible for the high frequency change in the stock market. So on the other hand, the information arrives continuously, and it actually has a potential in the market, which is very high. The second premise of our model is that information-driven volatility requires a risk premium. The empirical evidence of the macroeconomic announcement premium provides empirical support for information-driven volatility to require a risk premium. The most easily identifiable information events are macroeconomic announcements empirically, the recent literature has shown that a large fraction of the activity risk premium is realized on only a small number of macro announcements. So from a theoretical point of view, I and Benzel 2018 demonstrate that the representative agent models generalizing risk sensitivity in practice is actually needed to account for this macro announcement premium. So our model is built on this generalized risk sensitivity condition, and we further demonstrate that information-driven volatility affects this compensation and generates this return predictability, which actually explains empirical positive. So let me talk about the model next. Our model is a dynamic model with learning. And we start with a recursive prefix with constant IES and a constant risk aversion. And we assume the aggregate consumption follows a geometric random walk with time varying drift, the same way as the standard line is. And we assume that the description XT is a latent variable modeled as a two-state Markov chain with the following transition. So to highlight the information-driven volatility, right, channel, that is our point of the paper, we intentionally shut down the stochastic volatility of the macro fundamentals. So the sigma is constant. Not because we think it is not important, but because fundamental volatilities are unlikely to affect the short horizon volatility of the stock market. We would like to illustrate how far we can go with the information-driven volatility only. The aggregate stock market is a claim on the dividend, and the dividend is modeled as a continuous time reverting process. And we have this leverage to C, and we find out X here. And next, I would like to talk about the signal. Okay, so on this discrete announcement, T2T3T, investors observe this public signal about X. And with the probability mu, the mu means is the probability of revealing the truth of the X. Mu is 0.5. It means that announcements are completely uninformative. Mu is 1 means announcements carry perfect information about X. So we further want to make some assumptions. We say mu can totally take two values, mu low and mu high, and you can change over time is ID. And also, I want to, so in addition to this public signal, between announcement days, we assume that investors can observe something itself to infer about this latent variable. So here is a timeline plot for 30-day announcement cycle and a source of information about fundamentals. So now let me plot a policy function. So let me plot this policy function from the model to illustrate this basic idea or basic implication. The horizontal x-axis is the informativeness of the public. Our model has two key inputs. Okay? The first one is as mu becomes higher, the announcement becomes more informative. As mu becomes higher, announcement becomes more informative. And this is associated with higher premium realized on announcement day and larger reduction of the implied variance timeline.
Just for your information, you got roughly 7 minutes.
Okay, thank you. And the other one, as I said, the other implication from our model is that as mu goes higher, as the information gets more informative, and so it is associated with lower expected return in the future, a lower variance going forward. Okay. So as you can see, the key state variable of the model is the informativeness of microanalysis. So empirically, how do we measure? Empirically, we use implied variance. We use implied variance reduction to reflect this measure of informativeness. Option implied variance option implied variance reflects this market with neutral expectation of the volatility before the maturity. So therefore, implied variance before announcement include the variance on announcement day, and implied variance after announcement does not include information about announcement day. So the difference between the two reflects how informative this announcement. Okay, next we calibrate our model, and there are the details about model matching. I'm going to skip this slide. I'm going to go directly to the next slide about how to examine our quantitative implications of our model. So first, we design and conduct empirical tests for several implications from the model, and then we replicate the same thing in the model simulation. So we have two key implications here, okay? And the first one is more informative of the announcement is associated with higher announcement day return and higher reduction of implied. And the second implication is that the more informative of the announcement are associated with lower return and lower variance in the future. And finally, we're going to replicate our model, the volatility managed portfolio. This volatility model followed by Moore, 2017. Okay, the first one. So let me test our theory of this information-driven volatility. We focus on most identifiable information events in the data. So that is FOMC announcement, right? To test the implication of our model on the announcement day return predictability, we really need something that would extract a measure of informativeness before announcement. So our empirical measure of informativeness is based on option implied variance. And option implied variance constructed from the option prices covers both the upcoming announcement days and also the subsequent days without it. So assuming all non-announcement NI, okay, assuming all non-announcement realized implied variance are constant, and if we have both the 90 days and 30 days implied variance, we can solve these two linear equations to back out announcement day implied variance. So back out this AI. So once we have the AI, and we know that the volatility can be high because the period of this is actually a high uncertainty period. So we want to normalize this IIV by the past realized period. So then this is a measure of information. So I take the difference about this implied announcement realized implied variance, and then subtract it with the past realized variance and hold for high circuit volatility and circuit period, and then construct this informative.
3 minutes.
This measure is done before, okay, before. Okay, here comes my empirical result. So the first premises exercise we test about is use this informativeness to predict announcement day returns and announcement day implied variance reduction. As you know that daily return is firstly part of a very incredibly difficult to predict, but we can use our informativeness measure. We can have a 15% R squared for the return probability regression, and or the reduction of variance is also interesting. And we can replicate a similar pattern in our model. And moving on, the second exercise, a second implication. So because right now we are standing at announcement day, we can directly use an implied variance reduction as a measure of informativeness. We can use this variance reduction and predict what's going on in the future. So in this case, we use realized variance in the future, 1 day, 2 day, 3 day, and all the way to 2 months. You see as we are, as these implied variance reduction becomes larger, and the realized variance in the future becomes smaller. And we replicate the same, so we do the same regression, but replace this realized variance with return. And we basically have a similar conclusion here. The more reduction of this implied variance, the more uniformity of this announcement, then we're going to start to see lower return. So we also replicate similar patterns in our model. So then finally, the last piece of the integral exercise we did was we tried to replicate this volatility managed portfolio in our model simulation. And we actually find that there is an extra excess return about 1.68% of this volatility managed portfolio in our. So very last page, I want to conclude about our paper. So let me summarize traditional theories with stochastic volatility model, okay, in the fundamentals imply a positive relationship between realized volatility and expected return. Well, the stochastic volatility in the fundamentals is indeed important for us to understand long horizon risk compensation of this stock market, but unlikely in the short horizon. So this paper highlights the distinct picture of this information-driven volatility. Unlike the fundamental volatility, the information-driven volatility can induce a negative relationship between past realized volatility and expected returns over short. Okay, that's it for me.
Thank you very much. And basically right on time. And the discussant is Nicole Branger.
Thanks for having me, and thanks for giving me the chance to discuss this paper. The paper is about volatility-related puzzles in asset pricing models. As Ley pointed out, we have excess volatility, that is, the volatility of returns largely exceeds the volatility of fundamentals. We also have a negative relation between past realized volatility and future returns, which is also linked to this volatility-adjusted strategy of Moreira and Muir. We have that the variance risk premium predicts future returns. The puzzling fact is that none of its components, neither implied variance nor realized variance, does on its own predict future returns. I could continue this list. I leave it at these puzzles. What this paper does is it focuses on the second puzzle, namely the negative relation between volatility and returns. The focus of the paper is on announcements, and the main point of the paper is that revelation of uncertainty can explain what we see. I have structured my discussion by using this timeline where we have t-2, t-1, and t. We observe, let's say, daily returns over these intervals. We observe realized variances calculated from intraday data, and we also see implied volatilities where I have used a 30-day window into the future. That is, I am basically looking at the VIX. Now, what is the relation between uncertainty measured by realized or implied variance and returns which I see? A standard asset pricing model tells me that volatility, stochastic volatility, has a positive autocorrelation. That is, a high realized variance in the past predicts a high realized variance also in the future, and as a contemporaneous relation, a high realized variance comes with a high expected return. That is, in the traditional asset pricing model, the relation is positive. Now, the empirical finding, at least for shorter time periods, is that a high realized variance in the past predicts low returns going forward. And the question is, what is going on here? The authors suggest a model based on an endowment economy. Consumption follows a straightforward diffusion process, constant volatility, and a stochastic drift. The first main point is that the drift, which follows a two-state Markov process, is unobservable. The second point is, at the announcement dates, we get a signal about the true drift. The precision of the signal changes over time, but it is observable and it's known to the investor. The investors have recursive preferences with a preference for early resolution of uncertainty and, which is more important for announcement returns, generalized risk sensitivity. Now, let's look at the role of volatility in more detail in this model. Consumption volatility has two reasons. The first reason is the diffusion component that's constant, that could easily be generalized, and that's not our main point. We are after consumption uncertainty that is generated by the stochastic drift, which can be either high or low. Now, the stochastic drift is unobservable, and the investor learns about it. He learns from consumption continuously over time. Again, that's not too interesting here. And he learns from announcements. At discrete points in time, there is a reduction of uncertainty and an information about, is the drift high or low? Now, what A and Bansal have shown in an earlier paper is that the average announcement return is positive. And as also pointed out in this paper, this is basically driven by what I would call the continuation utility component of the pricing kernel, which we have for generalized risk aversion. But what does it imply for the relation between uncertainty and returns? Well, we now have an announcement date in this figure. What is happening at the announcement? At the announcement, I get information about the future drift and thus about the future behavior of consumption. That is, a lot of information is revealed at the announcement date, and the uncertainty I have about consumption going forward, that is reduced. That implies I have a large realized variance at the announcement date, and I have a rather small implied and realized variance after the announcement date. Stated differently, part of the uncertainty about future consumption is revealed right now, brought to the current announcement date, and taken out of the future. Well, what that implies is an announcement return that is on average positive, and more important here, the realized variance which comes with a low expected return going forward. And in that way, we have our relation. A high realized variance at the announcement induces a low realized variance going forward, and therefore a low expected return. That is, the announcement breaks the positive autocorrelation of variance, which is assumed in standard asset pricing models. That's the basic mechanism of the model. Now, let's look at the empirical evidence. What I show is table 4 from the paper, where the authors give me the reduction in implied variance, both in the data and in the model. At the announcement date, that's the intuition, implied variance has to be reduced because at the beginning of the day, it still includes the huge uncertainties that will be revealed. At the end of the day, this huge uncertainty is taken out, volatility should be lower. That's true for the median. I see a reduction in implied volatility. However, in around, let's say 30% of the cases, I see an increase in implied volatility, a negative reduction. And the question is, what's going on? What was particularly surprising for me is that we also see this not only in the data, but also in the model. One conjecture I have, without having tested it, is that we might see an increase in uncertainty when we move to a bad state. So good and bad states differ in the persistence of the current drift realization. If I have a state with a high drift, a good state, this drift is really persistent. That creates a low uncertainty in the future. If I am in the bad state, this drift is less persistent. That creates a high uncertainty in the future. Now, when I move to a bad state, uncertainty in the future increases, coming together with a negative announcement return. And the question is, can that explain that in around 30% of the cases, I see actually an increase in implied volatility? Would there be empirical evidence for this relation, or what are alternative explanations for what's going on here with implied volatility? Second set of comments refers to, let's say, the predictive. The authors use several tests to see whether their model is in line with the data. They use the implied volatility component of the announcement day, which is extracted from the term structure of implied volatilities, to see whether that predicts announcement day returns and reductions in implied volatility. It does. They use the change in implied volatility over the announcement date to see, does that predict future returns and future realized variance? And it does. And they use the variance risk premium, which is implied volatility for the future minus realized variance from the past, to see whether it predicts future returns, and it does. I've put variance risk premium in quotation marks here because we are not interested in the risk compensation component of that term. We are interested in the difference between volatility going forward in implied volatility and volatility referring to the past with realized variance. Now, the tests are done as predictive regressions.
That's fine.
Yeah, thank you. We regress the future return and the future realized variance on the change in implied volatility, the reduction we should see, on past realized variance and current implied volatility. When I saw this regression, I started to think about, why do I have implied volatility at t as a control variable instead of, see here, implied volatility at time t minus 1? Well, I can rewrite the equation, and that gives me, as a coefficient, I should look at not beta 1, but beta 1 minus beta 3. I could again rewrite that and look at not the reduction in implied volatility, but the variance risk premium, and look at what does that imply for future returns and future realized variance. To refer to the figures, the main point is, if I have a high variance on the announcement day, I have a low variance going forward and no expected return. Now, I can measure that empirically by looking at the realized variance on the announcement day. I can also look at the difference of implied volatilities after the announcement and before the announcement. Or I could look at the variance risk premium as the difference between implied volatility after the announcement minus realized variances before and including the announcement. In all cases, I am after the amount of revealed information. Now, the question is, which of these alternative measures is best? So my suggestion is here to run kind of a horse race between these predictors and to comment on the question, what is really the difference between these alternative measures? What can we, for example, in addition take from the variance risk premium by observing that there is also a risk compensation part in it. Can we somehow use these different measures to extract some more information? I am coming to my last comment. I want to link what you find to the puzzles. We have a positive announcement return on average. That was explained in a former paper. We have a negative relation between current realized variance and future expected returns. That's explained in this paper. And we have, to look at one further puzzle, a negative relation between idiosyncratic variance and expected returns. The current paper is silent on that. And that brings me to the question, or to the suggestion to see, what does this paper imply when we go to the cross-section? So when we go to the cross-section, we can have information about systematic cash flow components. Returns should then simultaneously increase or decrease, and we should see a high correlation when we see a high variance, both driven by announcements. We can have idiosyncratic information which should not be priced. We can also have a stochastic timing of announcements, because that's not all at only known dates, where the results should still go through. So my question here is, can you bring the model to the cross-section? What does it imply? And what does it, for example, tell you about idiosyncratic volatility and that volatility being priced? I come to the summary. It's a very interesting paper with a new twist to the focus on the role of information. It looks at announcements and revelation of uncertainty at the announcement day. It explains the counterintuitive relation between volatility and returns, and it has a high potential for future research and extensions. That's it from my side. Thank you very much.